Greetings to all and welcome to this lecture. We are in module 6, 4 terminal MOS structure, lecture number 1, a graphical interpretation. In this lecture, we will see how we can define the MOS transistor physics based on the graph plotted between minus Qi dash versus psi s, where this is nothing but inversion charge. We will also see how we can relate the surface potential, charge and current with respect to position along the channel. These are the learning outcomes of this lecture, which tells us the symmetry of the MOS transistor, which also give you an idea how we can relate the surface potential charge as a function of x or position along the channel. Let's do a quick recap. In the previous lecture, we found that our derived equation of IDS comprises IDS1 plus IDS2, where IDS1 and IDS2 is nothing but the drift component and the diffusion component, which is a function of psi s0 and psi sl, where psi s0 is the surface potential measured at near source channel junction by ignoring the edge effect. So, this is psi s0. Similarly, if this side is drain, this voltage is psi sl. We found a closed form equation of psi s0 and psi sl, and we said that we can use some analytical approximation to solve these equations. Further, we have seen that what will happen when we increase VDB or VDS, then how the surface potential at the drain side reaches to psi SA, which is nothing but a function of VGB, and will get saturation. We have also seen that the current is nothing but some function which is a function of VGB and obviously VSB and VDB. In addition, we can rewrite as psi SL minus psi S0. So, this component creates a horizontal field. Finally, we concluded our previous lecture with the claim that we are following gradual channel approximation, meaning the electric field in x direction is to be considered very small as compared to the electric field in the y direction, where the x direction is from source to drain along the channel and y direction is in this side. Now, let us see how we can explain our MOS operation by using the graph plotted between minus Qi dash and psi s. We know that Qi dash can be written as minus Cox dash into VGB minus V flat band voltage minus psi s minus gamma root psi s. This equation we have derived many a times using potential balance equation. So, if we draw a graph between minus Qi dash, then this quantity becomes plus. So, let us see the few parameters which is mentioned in the graph. If my surface potential is 0, then minus Qi dash is nothing but Cox dash into VGB minus V flat band. It means minus Qi dash is nothing but this value which is mentioned here. Now, what will happen if my Qi dash will be 0? So, I will get the maximum limit of the surface potential, which is nothing but keeping this is equals to 0, this is minus Cox dash into VGB minus V flat band voltage minus psi s minus gamma root psi s. So, ultimately you remember you can solve this equation as psi s plus gamma root psi s plus VGB minus V flat band voltage, and it ended up with a surface potential of psi SA, which is nothing but minus gamma divided by 2 plus square root of gamma square by 4 plus VGB minus V flat band voltage whole square. So, in this graph we finally got the two end point of these graph, and below which we will draw our graph. We also know that qi dash and surface potential can be plotted as a function of exponent. You remember in module number 2 we derived a closed form equation of qc dash by writing this equation signum psi s square root of 2 into q into na into epsilon s with contribution of wholes, which is nothing but phi t exponential of minus psi s by phi t plus psi s minus phi t. This is the contribution of whole. This is the contribution of immobile ions, and e to the power of minus 2 phi f by phi t e to the power of psi s by phi t into phi t minus psi s minus phi t. So, by doing some approximation, we concluded that we can simply plot qi dash with respect to psi s, and it seems like this. That is what we are plotting, qi dash for different values of psi s, keeping VSB at source side and VDB at drain side. So, let me draw the schematic of MOSFET as well for sake of simplicity. So, this is N plus, this is N plus, here you have gate, this is drain and this is source. We are applying a voltage as VSB this side and VDB this side. So, ultimately we got two lines which shows the relation between qi dash and psi s0 and qi dash and psi sl. It is clear and already mentioned in previous lectures that psi s0 is nothing but surface potential measured just at the source channel junction, and psi sl is nothing but the surface potential measured here by ignoring the edge effect. Now, if you see clearly, this intersection point is nothing but the solution of the equations written in terms of qi dash and psi s. This surface corresponding to this surface potential, this charge can be defined as qi dash 0, and corresponding to this surface potential, this can be defined as qil dash, meaning the inversion charge present here near the source and channel junction is qi dash 0, and the charge present near the channel drain junction is qil, corresponding to surface potential psi sl and surface potential psi s 0. Now, if we see carefully the difference between this, meaning qi dash 0 minus qil resembles something. If you see our previous equations of IDS2, then IDS2 can be written as W by L mu into phi t into qil dash minus qi0 dash, and this was nothing but a diffusion current component or mean of diffusion current, right. Here, as this x is having a negative sign, so you can take negative, ultimately you will get the same difference of qi dash L minus qi dash 0. So, the difference between this point and this point reflects IDS2, which is nothing but diffusion current. Now, what this reflects? If you calculate this blue shaded region, then ultimately you are doing integration from psi c0 to psi sl, and you are integrating the charge. If you remember, this is a part of our current IDS1, where IDS1 can be written as W divided by L mu into integration psi s0 to psi sl. It means the area of this region will give you the drift current. So this is nothing but IDS. Now let's analyze the graph for different values of VDB, meaning you take a MOSFET here, N plus, you are applying VDB keeping VSB constant. Let us consider this graph is plotted for a fixed VGB. It means initially you applied the VGB in such a way that sufficient amount of inversion charge is present in the channel and you are in strong inversion. Now you are increasing VDB. If the VDB is increasing, ultimately the increase in VDB increases your surface potential. So if I plot VDB versus psi SL, so the surface potential increases, and after a certain point it gets pinned to a value of psi SA. So this region of operation is strong region, this transition is moderate, weak and depletion region. We have seen already this graph earlier. So what we are doing, we are increasing VDB. By increasing VDB, the surface potential psi SL will increase at this edge. If the surface potential increases, means this point will go at right side. If the point is shifted, it means what? The area is increasing and hence IDS1 increases, correct? Similarly, if you go on increasing psi SL, ultimately the area of this trapezoidal increases and IDS1 increases, which is nothing but psi SL minus psi S0 component increases and causes drift current to increase. Now what will happen if you increase VDB beyond a certain point? So beyond a certain point, the increase in VDB increases the surface potential and fixed to a value of psi SA. So that is what psi SA is nothing but now psi SA. Psi SL is now become psi SA. If that is become psi SA, ultimately the area of this trapezoidal become a triangle. Now beyond increase of VDB will not affect the psi SL because the psi SL is fixed to value of psi SA. Even if you increase the VDB, there is no change in the surface potential. Similarly, if you see this point, this is QI0 and this is QIL dash. So as this point is going towards this side, QIL dash approaches to 0. So we have seen two factors, that when you increase VDB, ultimately the surface potential at this side is pinned to value of psi SA, as well as the QIL approaches to 0. But to maintain a current continuity, the overall current is nothing but the area of this thing, which is nothing but constant, and hence we can plot the output characteristic as we have seen in previous lecture. If we are plotting output characteristic with respect to VDB and IDS, let us say this is VSB. So a small increase in VDB increases the area and hence the current increases linearly. But after a certain point, the increase in VDB is not changing the surface potential and hence it is not changing the surface potential here, and the surface potential is pinned to psi SA. So the change in charge is fixed. We have seen that when VDB increases beyond a point, then the surface potential is pinned to psi SA, and at that moment the current is constant because the trapezoid is now become a triangle. So this area is constant. Now how I can increase the resultant area? For example, if I increase VGB, then what will happen? If I increase VGB, because of this dependency, this point is shifted like this. Let us consider this is VGB1 and we are plotting for VGB2. So this point is for VGB2 where VGB2 is greater than VGB1. As you are increasing VGB2, right, then this surface potential is also increases because if you remember psi SA formula, it is nothing but minus gamma by 2 plus square root of gamma square by 4 plus VGB minus V flat band voltage, and hence the factor of VGB is coming in this equation as well. So this point will also shift like this, and hence you get a new boundary which allows you to increase the VDB in such a way such that you can get some non-saturation part here, and hence if you increase VGB, your drain current will increase because the area is increasing, as well as the saturation point is get shifted towards right hand side, meaning for the higher value of VDB the saturation takes place. So this is a graphical representation which will give you the idea how we can understand the MOSFET behavior in non-saturation and saturation region of operation. Let's analyze the symmetry of this MOS transistor. We said that we do have two terminals, N plus, and here this is source terminal, this is drain terminal, and we have a gate terminal here. We actually formulated a drain to source current in terms of IDS1 and IDS2, where IDS1 is nothing but mu into COX dash W divided by L into VGB minus V flat band voltage into psi SL minus psi S0 minus half of psi SL square minus psi S0 square minus 2 by 3 gamma psi SL to the power 3 by 2 minus psi S0 to the power 3 by 2. So this was the component IDS1, and another component was IDS2, which is nothing but mu into COX dash W divided by L into phi t psi SL minus psi S0 minus plus there is phi t gamma psi SL to the power 1 by 2 minus psi S0 to the power 1 by 2. It means if you see the function IDS1 and IDS2 is nothing but a function of psi SL and psi S0. So I can rewrite these equations in such a way that W by L is common, and I can write it is dependent on some function of psi SL minus some function of psi S0. If I interchange these terminals, let us say if I say this source is replaced by drain and this drain is replaced by source. So in this equation nothing is going to be changed, because earlier I was assuming this is my psi S0 and this was psi SL, but now this becomes psi SL and this becomes psi S0. The only thing is the direction of the current earlier was from drain to source, now the direction will get changed. So you need to have a negative sign when you are just swapping the terminals. That is what we say that MOSFET is a symmetric device. Now let us see how we can relate the surface potential, charge and current with respect to position. For example, we have a MOSFET and we formulated all those equations between 0 to L. So this is N plus, source terminal, drain terminal, we have an oxide and gate terminal. What we said is at point 0 our surface potential is psi S0 and the inversion charge is Qi dash 0, whereas at point L, which is near to drain, surface potential is psi SL and the inversion charge is Qi dash L. We derived this equation considering that inversion region is present throughout the channel, and we assumed a small factor of delta x and we integrate between 0 to L. Now let us assume if the channel length is large enough and I am pointing a point here at the middle or somewhere x, somewhere in between x or somewhere in the channel. Let's say this point is A. If I closely see between 0 and A, this device is nothing like a MOSFET. So, I can define the surface potential at this point, and I can also find out the inversion charge at that point if I know the overall formulation. So, what I will do, if I know the equation which is a function of psi SL and psi S0, I can define that a MOSFET between 0 and A works the same, then IDS can be written as W divided by X. So, here this is a function of X into some function of psi S X. So, this is a surface potential which is a function of X at some point A and psi S0. You take a note here that we are considering that the source end or the 0 location is as reference. So, we can rewrite this equation as this. Considering the current is common throughout the channel, and hence we can solve this equation to get a relation between surface potential with the position x. So, along x, if we plot a surface potential, then we will get this curve. Let us understand how we plotted the surface potential as a function of x. Suppose at this edge you are in strong inversion. So, there is some surface potential which is psi S0. Now, if you consider VDB is equals to VSB, for the same VGB value you will be in strong inversion at the drain side. It means there are same amount of charges here, the same amount of charges here, and hence the surface potential measured at this location will be same as the surface potential measured at this location, until and unless your VDB equals to VSB. It means there is no flow of charge between the channel. Now, the moment you increase VDS, then what will happen? The surface potential at this side will increase. If the surface potential at this side will increase, then there will be a drift component comes into picture, meaning psi SL minus psi S0 will come into picture, because you are not increasing this side voltage, you are keeping VSB as fixed, right. So, the surface potential is increases at that point, and this varies in between 0 to L. This is nothing but the surface potential as a function of x. Similarly, we can relate the inversion charge as a function of x. How can we do that? That we will find the surface potential as a function of x, and then we will use the inversion charge equation which is a function of surface potential. As we have seen earlier that Qi dash can be written as minus Cox dash into Vgb minus V flat band voltage minus psi s minus gamma root psi s. So, if I know the surface potential as a function of x, then by using this function I will put back into the inversion charge equation, and I can relate the inversion charge as a function of x. Now, I can define two quantities if I know how my inversion charge varies with respect to x, and I also know how my surface potential varies with respect to x, then I can simply find the slope. It means how dqi dash by dx varies, or how d psi s by dx varies between the source and the drain end. These are important parameters to find out drift and diffusion component. If you see the drift component or IDS component, which is nothing but mu into W into minus Qi dash into d psi by dx. We have seen this many a times in our previous lectures. So, this is IDS1, or you can say this is drift component. Now, how the drift component varies along the channel? If you see carefully, when you are moving from 0 to L, the change in the surface potential is increases, right? The change in the surface potential or the gradient of surface potential with respect to x increases. However, at the same time the inversion charge is decreases, because when you are increasing VDB, this side surface potential is going and pinned to psi SA value. It means the inversion charge will approaches to 0. So, the dominant factor is Qi dash, which is approaching 0, and hence you can figure out that the drift component along the channel will decrease. So, drift component will decrease. Similarly, we can find out what will happen to the diffusion component. In a diffusion component, we found that diffusion component can be given as mu into W into phi t into dqi dash by dx. So, though qi dash is decreases along the channel because you are increasing VDB, but the gradient will increase, meaning when you are going from 0 to L, the qi dash will decrease like this. However, if you find out the gradient, the change in charge with respect to x and mod, ultimately you will find that it will decrease somewhere in the middle and then it will increase to maintain the current continuity, because at this side the drift is reducing and hence the diffusion should increase to maintain a constant current. So, we will find that the diffusion current along the channel will increase and the drift current along the channel will decrease. So, in such a way you can find out how the surface potential, charge and current can be calculated in terms of position. If x is the position in horizontal direction, meaning you are moving from source to drain. Let us get an insight of MOSFET again in terms of energy band point of view. We have already seen this energy band diagram viewpoint in last lecture, but let us get a new insight related to the drift and diffusion. Let me explain again that if you have a MOSFET as N plus P and N plus, and if your applied VGB is small enough, then there will be a potential barrier exist between N plus and P. That potential barrier can be given by Q times of phi Bi, meaning the electron which is present in the conduction band of the N plus faces a difficulty to go from source to channel because of presence of this barrier. This barrier height is nothing but phi t log of Na Nd by Ni square. Now, what will happen if you apply VGB? If you apply VGB, ultimately the surface potential will increase, and hence from 0 surface potential, which is represented by A dash, you are going to a higher surface potential which is B dash. In this, till this case, we are assuming that VSB is equals to VDB, and hence you are just creating the inversion charge here, and the charge will not flow because there is no potential difference between source and drain. So, the potential energy goes down and represented by B when you applied VGB. Correspondingly, the surface potential is B dash. Now, let's for that particular fixed value of VGB, you are increasing VDS or VDB. The moment you increase VDS, this surface potential psi SL is increases and ultimately it is pinned to psi SA value. So, the psi SL is ultimately pinned to psi SA value. So the moment when you increase VDS, the bending will be there in the potential energy, right? It means the conduction band goes lower. We have discussed this part in module 1 as well. When you are applying a positive voltage, the band diagram will go downward, and hence that's what it is, because this shift is given by Q times of VDS. So the voltage whatever you are applying here, the band will go down. If you see carefully, there is a bending in the conduction band, meaning there is a gradient exists in the conduction band along the x, and we know that 1 over q dEc by dx is nothing but what? Electric field. If there is a gradient in the conduction band, there is an electric field in this direction. This electric field is actually pulls this electron towards the drain end, and hence here in this region drift takes the hold, right? It means that once the carrier are reaching this channel position or in the channel, ultimately it gets attracted because of the drift, and the current mechanism is captured by the drift phenomena. Interestingly, if we see carefully about this position, or you can see this position, when you apply VGB, the conduction band get lowered, but the gradient of the conduction band is almost 0. So dEc divided by dx over 1 over q is almost 0. This is not affected, and hence at this region the electric field should be 0. Then how the carriers are moving from source to channel? If there is no electric field, but if you are applying VGB, you can see in the forward bias PN junction, when you apply the P type, the forward voltage in the P side, then there will be a barrier lowering, and hence the charge transfer from P side to N side or N side to P side by diffusion. That is what happening here. The carrier from source to channel will go by diffusion. The moment carrier enters into the channel, the drift takes the hold. And so this is what the MOSFET operation is. When you apply VGB, the slight change in the surface potential at source channel junction happen. So if I want to explain this in terms of surface potential, if you increase VGB, the surface potential is linearly increasing. You remember this graph, we have plotted that until weak inversion, the surface potential is linearly dependent on VGB. So when you increase VGB, the surface potential is linearly increases, right? And we know that the barrier lowering or the carrier density across the barriers is dependent upon exponential of that barrier height. So let us consider you are applying VGB. This VGB changes linear change in the surface potential, and hence the barrier lowering is captured by exponential of psi s by phi t. Because of the linear dependency, I can simply write e to the power of VGB divided by phi t. It means under weak inversion, the drain current is given by exponential function of VGB under weak inversion. But in the strong inversion, when VGB is enough, then what will happen? The charge and the surface potential are logarithmically related, meaning you can say it follows a linear trend after certain point of VGB, after certain point of VGB where strong inversion takes place. So this is IDS. So let me summarize this lecture. We have seen that when source and drain potentials are interchanged, then channel equation remains the same except the direction of the current, meaning the MOSFET is a symmetric device. We have also find that the drain current, which is nothing but the sum of IDS1 and IDS2, can be expressed by drift and diffusion components. To ensure the continuity, where there is drift, there will be a lesser diffusion, where there will be a diffusion, there will be a lesser drift. We also find from the band diagram point of view that the carriers will cross the barrier at source channel junction using diffusion phenomena, and the moment the carrier comes into the channel, the drift takes the hold. So we'll stop here for today. Until then, take care.